Simplify roots of negative numbers. If we have just our counting numbers, 1, 25, 300, there's a void. If I had $2, I lost $5, I'd be down to $3. So that's where my negative integers come in. But there's a void. Maybe I go ahead and want to say, gosh, half the population is going to fulfill some demographic. You know, maybe half of the population is all female. So now I have my rational numbers. But the rational numbers also fill a void. You know, for example, if I have x squared equals 2 and I want to solve for it, I get x is equal to plus or minus the square root of 2. So now I have my irrational numbers. So I have all my real numbers, but these real numbers have a void as well. And the void is coming back to where we solve. And if I was to solve x squared plus 1 equals 0, I would get x squared is negative 1, and x would be plus and minus the square root of negative 1, and I just want to take a look at the square root of negative 1. That's the root of a negative number. And what I do is I use I to represent the square root of negative 1, so that if I square I end up with negative 1. So an imaginary number is a complex number that can be written as a real number multiplied by the imaginary unit I. So this number I is an imaginary number. When squared, the imaginary number will yield a negative real number. If I was to square I squared, I get a negative 1. So we can simplify imaginary numbers by remembering to write them with an I. For example, I'd write 10i. I wouldn't write the square root of negative 100. I would simplify it. Instead, I would write the square root of 100 times the square root of negative 1, and the square root of 100 is what? The square root of 100 is
10.
10. So I would have 10 times I, and that's what I had right here. So let's see if we can go ahead and simplify the given imaginary number. We're going to start by taking a look at the square root of negative 10. And I'm going to rewrite it. How am I going to rewrite it? I'll have the square root of
10
times the square root of
negative 1.
Very good. And what is the square root of negative 1?
I.
I. So this becomes the square root of 10 times?
Times I.
Times I. And you're always writing these as a real number times I, in that order. Let's take a look at the square root of negative 9. How would I rewrite that?
The square root of 9 times the square root of negative 1.
Very good. The square root of negative 1 is?
I.
I. And now I want to simplify further. Square root of 9
Is 3.
is 3, and so I could rewrite this as 3.
I.
3i. Well, let's keep playing this game. This seems awfully fun. I would like to rewrite the square root of negative 24 as
the square root of 24 times the square root of negative 1.
And the square root of negative 1 is
I.
The square root of 24, is there any perfect square that's a factor of it? Like 0? No. 1? No. 4?
No.
No. 4 is not a factor of it?
4 is a factor.
4 is a factor. 4 times what is 24?
4 times 6.
All right, so let's rewrite the square root of 24 as the square root of 4 times the square root of 6. And then the square root of negative 1 is?
I.
Any further simplification I can do, and I'll give you a hint by writing another equal sign.
The square root of 4 is 2.
Very good. So now I have 2 times the square root of 6i. And we'll go ahead and take a look at one more, and then we're done. And the last one we're going to do takes a look at the negative 2 times the square root of what? Square root of negative 18. So I want to rewrite it. I'll do the easy part, negative 2. Your turn.
Times the square root of 18.
Very good.
Times the square root of negative 1.
Okay. What is the square root of negative 1?
It is I.
I. Can I rewrite the square root of 18 with a factor that's a perfect square?
The square root of 9 times the square root of 2.
Very good. And then the square root of negative 1 you've already told me is I.
Right.
What is the square root of 9?
3.
3. So it looks like now I have negative 2 times 3 times the square root of 2i. Do you see anything else I can do?
Multiply the negative 2 and the 3 to get negative 6.
Very good. So I get negative 6 times the square root of what? Square root of
2.
2 times
I.
I. Thank you. Thank you. add or subtract complex numbers. Just like with real numbers, we can perform our calculations with complex numbers. The way we do this is, if we're adding or subtracting complex numbers, we will add the real components and we'll go ahead and add the imaginary components. So when you add complex numbers, I'm just going to take two complex numbers like a plus bi and c plus di, and I'll add the real components, a plus c, and then I'll turn around and add the imaginary components, bi plus di. I'd probably do this by factoring out the I. And similarly, when I go ahead and subtract complex numbers, I will go ahead and subtract the real components and turn around and subtract the imaginary components. So let's go ahead and add these two complex numbers, 2 minus 5i plus 3 plus I. First thing I'm going to do is add the real components. What do I mean by that? What am I going to add?
You're going to add 2 plus 3.
Very good. And then I'll go ahead and add the imaginary components, which are what?
Negative 5i and I, 1i.
Very good. Now basically I'm combining like terms. 2 plus 3 is
5.
5, and negative 5i plus I is?
Negative 4i.
Beautiful job. And I'm done. We'll go ahead and subtract two complex numbers. We'll take negative 6 plus 10i and subtract 3 plus 12i. And again, the same set of questions. I first want to subtract the real components, so I will do what? I'll take a look at.
You'll take a look at negative 6 minus 3.
Very good. And then I'll go ahead and subtract the imaginary components.
Right, so you'll have 10i minus 12i.
Beautiful job. So my real component would be?
Would be negative 9.
Very good. My imaginary component would be?
Would be negative 2i.
Beautiful job, and I've subtracted two complex numbers. Thank you. We want to add 3 minus 4i plus 2 plus 5i. When you add two complex numbers, you add their real components, and then you add your imaginary components. So 3 minus 4i plus 2 plus 5i would be evaluated by adding the real components, 3 plus 2, and then the imaginary components, negative 4i plus 5i. 3 plus 2 is 5, and negative 4i plus 5i is I, and we end up with 5 plus I. Multiply complex numbers. Well, when we multiply a complex number by a real number, that's how we'll start, we'll use the distributive property and we'll basically simplify. For example, if I took the real number 4 and multiplied it by 2 plus 3i, I would distribute the 4. 4 times 2 is 8. 4 times 3 is 12, so I have 8 plus 12i. And if I went ahead and took a look at multiplying negative 2 by 2 plus 3i, I distribute the negative 2. Negative 2 times 2 is negative 4. Negative 2 times 3i is negative 6i. And I have my two results. Now I want to stop and think about the two results for a moment. I mean, not for very long, but I do want to think about it for a moment. If I take a look at 2 plus 3i and I plot it with a real axis and an imaginary axis, I would go over 2, I would go up 3, and I would go ahead and draw my representation of this complex number, 2 plus 3i. Now when I take a look at the result of multiplying that by 4, I ended up with 8 plus 12i, didn't I? So if I go ahead and connect and take a look at 8 plus 12i, I notice that I have 4 of these 2 plus 3i's, and that's all we're really doing. We're quadrupling the real and the imaginary parts. And similarly, if I go ahead and take a look at the effect of multiplying by the scale of negative 2, it reverses the direction and it doubles the length of this particular vector. So 2 plus 3i, I've already sketched in green. I'll re-highlight it here. Okay. If I reverse that particular length and sketch what? Sketch negative 4 minus 6i, then I would end up with a vector that would be right here. And notice that would be 2 of these 2 plus 3i's in the reverse direction. Next, I want to multiply two complex numbers. So I'll take a plus bi and multiply it by c plus di. And basically, I'm just going to use the FOIL method and simplify. So if I ran through this, I would go ahead and multiply my real components. Well, let's go ahead and do that. A times c would be ac.
Right.
And then with FOIL, what would the outside portions being multiplied look like?
ADI.
Okay, ADI. How about the inside?
And then, so it'd be plus CBI.
Okay, and I'll put BCI,
BCI.
alphabetical order just for now. And then how about the last? What would the last of the components look like?
Plus BDI squared.
Very good. Now a couple of questions for you. First is, what is I squared?
Negative 1.
Okay. The next is that if that's negative 1, do you see two real terms? What are the two real terms that you see?
See AC and negative BD.
All right, so I have AC minus BD.
Right.
That's the real component. Now for the imaginary component, if I go ahead and factor out an I from the two terms, what would that imaginary component look like in the form of a number times I? In this case, it would be?
It would be AD plus BC all times I.
Very good. Now, you're not memorizing that formula, certainly, but you're using this method to multiply two complex numbers, and what we're going to do is just that. We're going to multiply first negative I by 2 plus 3i, and then 2 plus 3i times 5 minus 4i. So let's start with just negative I times 2 plus 3i. I don't want to rewrite it as 0 minus I. It'd be lengthy. I'm going to go ahead and just use my distributive property to avoid the FOIL method. I'll multiply the negative I by what? Negative I by?
By 2.
By 2.
So that would give me what? It would give me?
Negative 2i.
Okay. And then negative I I'd multiply by?
By 3i would be negative 3i squared.
Very, very good. Now, why do I want to keep going? Why am I not done at this point?
Because I squared equals negative 1.
That's one reason, and that's the right reason. Is there another reason that's equally right? Is this complex number written in the proper form?
No.
No, it needs to be in the form of a plus bi. Very good. So let's go ahead and make that substitution. So we have negative 2i minus 3 times negative 1. And let's write my complex number in the form of a real component plus an imaginary component.
Sure. So you would have positive 3 minus 2i.
Very good. And now it's in the form of a plus bi. Finally, we'll go ahead and multiply two complex numbers both in the form of a plus bi and c plus di. I say we, but that's not a good choice of words, is it? You will do this. Let's use the FOIL method here. What will I multiply first?
2 times 5,
Which
is
is
10.
10. Okay, how about the outside pieces?
That would be negative 8i.
Very good. FOIL, inside pieces.
15i.
Okay, so plus 15i. And finally,
Minus 12i squared.
very good, the last terms, minus 12i squared. Now, I know you know what I'm going to ask you. I'm going to ask you what is I squared, and your reply is what? It's
It's -1.
-1. So what would my next step look like? We would have a 10. I'll do the easy part. Can we combine these two terms? What would they be?
That would be 7c. Or 7i. Sorry, I thought that was...
Plus 7i. Why is
Yeah.
it not a c?
Because it's imaginary.
It's an imaginary number, and I stands for
Imaginary.
imaginary, and it represents the square
The
root
square
of?
root of -1.
Beautiful. And then I have negative 12 times I squared, but you already told me I squared was what? It was?
-1.
-1. So my very last step is to combine the real components. that we see where? We see here and here, right?
Yeah.
So what am I going to have as my final answer in the form of a plus bi?
So you'll have 22
And that's 10 plus 12. Very
Yeah.
good. 22 plus
plus 7i.
plus 7i. Thank you very much. Let's multiply two complex numbers, 4 plus 3i times 2 minus 5i. Before we begin, let's remember that I squared is equal to negative 1. Now, the first thing we're going to do is we're just going to use the FOIL method. I'll distribute the 4. I'll have 4 times 2. And I'll have 4 times negative 5i. Then I'll go ahead and distribute the 3i. I'll have 3i times 2 and 3i times negative 5i. So let's simplify. 4 times 2 is 8. 4 times negative 5i is negative 20i. 3i multiplied by 2 is 6i. And then 3 times negative 5 is negative 15. And I times I is I squared. And I know what I squared is. I squared is negative 1. So now I have 8 minus 20i plus 6i minus 15 times negative 1. Well, let's combine like terms. I have 8, and this number here is actually a negative 15 times a negative 1, which is plus 15. So 8 plus 15 is 23. Combining the imaginary terms, I have negative 20i plus 6i. That's negative 14i. And when you're done, you want to write the answer in the form of a plus bi. That's what we've done here, 23 minus 14i. Divide complex numbers. We're going to start with learning about a complex conjugate of the complex number a plus bi. And the complex number conjugate is a minus bi. And what you do is you just simply change the sign of the imaginary part from bi to negative bi. The real part remains unchanged. So when a complex number is added or multiplied by its complex conjugate, the result is always a real number. So if I took a look at 2 plus 3i and I just wanted to know the complex conjugate, reminding myself I'm just going to change the sign of the imaginary portion, that complex conjugate would be what? It would be
2 minus 3i?
2 minus 3i. Very good. How about 3i? What would the complex conjugate be there?
Negative 3i?
Negative 3i. It's kind of like having 0 plus 3i, and now you write it as 0 minus 3i. How about 2? That's a complex number. It's 2 plus 0i. What would its complex conjugate look like?
Just 2.
Just 2, because then you'd have 2 minus 0i, which is just 2. Now, why did we want to stop and learning about complex conjugates? Well, strangely enough, the answer lies in how we write our complex number. It's written in the form of a plus bi. So it's a real number plus a real number times I, which I'm sure you know. But what's key is that that imaginary part is a real number times I. So when I divide two complex numbers, I start with an I in the denominator. And that's not the form that we want. So we don't want I in the denominator at all. So to get rid of that particular term, we multiply our numerator and denominator by the complex conjugate of the denominator. So what I'll do is I'll multiply my numerator and denominator by the complex conjugate of 2i, which is negative 2i. It's like multiplying by a 1, so I don't really change anything. And now I go ahead and simplify. So I'll distribute the negative 2i, rather you'll distribute the negative 2i. 6 multiplied by negative 2i is
Negative 12i.
in harmony. Love it. Negative 4i times negative 2i.
8i squared.
Very good. Negative 4 times negative 2 is positive 8. I times I is I squared. And then when I take a look at 2i times negative 2i, I end up with
4i squared. Negative 4i squared.
Negative 4i squared. Very good. And remember, I squared is equal to what? I squared is equal to what? I squared is equal to
Negative 1.
Negative 1.
negative 1. So are you seeing my denominator as a number that's a real number? My denominator is actually what? My denominator is actually
It is actually
4.
positive 4.
positive 4. Good. So I'm going to go ahead and rewrite. I'll have negative 12i, and then I have plus 8i squared, but that's the same as what? That's the same as
Minus 8.
minus 8. And again, that's because my I squared is negative 1. And then I'll divide by what? Divide by positive 4.
By 4.
Very good. And again, where'd that positive 4 come from? Negative 4 times negative 1. Now, our focus is always back here. We want to write the answer in the form of a plus bi. So I do have a little more work to do. First of all, I'm out of order. I would like to write the real term first, and at the same time, I'd like to simplify. Actually, I would like you to do that. So by my real term, I'm looking at this term right here. Negative 8 divided by negative 4 is?
Negative 2.
Very good. And I actually said negative 8 divided by negative 4. It's negative 8 divided by
Positive 4.
positive 4, which is negative 2. And then negative 12i divided by 4 is?
Negative 3i.
3i. Do I have a number that's written in the proper form of a plus bi?
Yes.
Very good. So I can stop. So that's why we multiply by the conjugate, because what it does, if we multiply the numerator and denominator by the conjugate of the denominator, it essentially removes the imaginary term, the term with the I, out of the denominator. So let's go ahead and take a look at dividing these two complex numbers. And the first step becomes, I'll multiply the numerator and denominator by the conjugate of the denominator, which would be what? Which would be?
2 minus I.
Beautiful. So when I do this, I end up with, well, let's go to the numerator first. First terms, 15 times 2 is?
30.
30. Outside terms, 15 times negative I.
Is negative 15i.
Okay, how about 4i times 2?
That is 8i.
Okay,
Positive.
Okay, positive. And then how about the last terms?
You'll get negative 4i squared.
Very good. Go to the denominator, do the same thing.
You get 4.
4.
And then minus 2i
Okay,
plus 2i
good.
minus I squared.
Very good. Now I have a whole bunch of questions for you. First off, remind me, what is I squared?
That's negative
Negative
1.
1.
And I see it in how many locations? I want to say I see it in
2 locations.
2 locations. I also notice that I can have a little bit of combining terms here. Go to the denominator, and negative 2i and positive 2i is what? It's
That comes
0.
beautiful. So the term with the I is removed from the denominator, which is what we wanted. So let's go ahead and take a look at our next line. And when we look at our next line, I'll have 30. Let's combine the imaginary parts. Negative 15i plus 8i is?
Minus 7i.
Okay, so we have negative 7i or minus 7i if it's in the form of the equation. Then how about that negative 4 times negative 1?
So that would be positive 4.
Positive 4. And we're okay why that's a positive, is that right? So negative 4 times a negative 1. Okay. And now let's go ahead and take a look at the denominator. And remember the negative 2i and the positive 2i, they canceled, right? And we were left with just a 4. And then I want to say minus the I squared, minus the negative 1. Well, we're not quite done. We don't have our complex number in the form of a plus bi. So in the numerator, combine the real parts, we get?
You get 34 minus 7i.
Very good. And in the denominator, see if I can make that look like a 7. There we go. Okay, minus 7i. What number's in the denominator?
Positive 5.
Positive 5. So I'll go ahead and put that positive 5 in the denominator so I can see my real portion and my imaginary portion.
Right.
So I have 34 over 5 minus 7/5 I, and when I say it that way, is this number in the right form? Is it in the form of a plus bi?
Yes, it
Yes.
is.
Yes, it is. We're done at this point. Thank you. Thank you. Find the complex conjugate. If I'm given a complex number in the form of a plus bi, the complex number is found by changing the sign between the real and the imaginary terms. So the complex conjugate of a plus bi would be a minus bi. When I look at the complex number 2 plus I square root of 5, I'll change the plus to a minus. So the complex conjugate would be 2 minus I times the square root of 5. If I want to find the complex conjugate of negative 1/2 I want to rewrite this as 0 minus 1/2 I, so I can clearly see the sign to change. I'll change that subtraction to an addition. So the complex conjugate would be 0 plus 1/2 I, which I'll just rewrite as 1/2 I. Let's divide 2 plus 5i by 4 minus I. Now when we're done, we do not want an I in the denominator. So when you do have an I in the denominator, and in this case we do because we have 4 minus I in the denominator, we multiply the numerator and denominator by the conjugate of the denominator, which means we change the sign in between the two terms. Why do we do this? Well, that's because 4 minus I times 4 plus I will give us 4 squared minus I squared. And we know I squared is negative 1, and we don't have any terms with an I. So my next step is to do just that. We'll take 2 plus 5i over 4 minus I and multiply the numerator and denominator by the conjugate of 4 minus I. That's 4 plus I. Well, if I multiply the terms out, I end up with 2 times 4, which is 8, 2 times I, 5i times 4, which is 20i, and then 5i times I, which is 5i squared. In the denominator, I'll end up with 4 squared, which is 16, minus I squared. Now, I want to go ahead and combine like terms, but I also want to replace I squared with negative 1, and I'll do that in 2 locations. So my next step is to take 8 plus 2i plus 20i, that's 22i, plus 5 times negative 1, that's negative 5, all over 16 minus I squared, which is negative 1. Well, let's combine like terms. 8 minus 5 is 3. So now I have 3 plus 22i in the numerator, and in the denominator I have 16 minus a negative 1, that's 16 plus 1, that's 17. And although I don't have any more terms to combine, I want to write my answer so that I see the real and imaginary parts. So the real part would be the 3 over 17, and the imaginary part, well, I have 22 over 17i. And now my answer is in the form of a plus bi. Let f of x equal x squared minus 5x plus 2, and let's evaluate f at 3 plus I, which means we'll take 3 plus I and substitute it into this function in 2 locations. So we have f of 3 plus I is equal to 3 plus I squared minus 5 times 3 plus I, and then plus 2. Now I want to multiply 3 plus I to 3 plus I. So if I do that, I'm going to go ahead and write out 3 plus I times 3 plus I. And if I multiply out the first terms, 3 times 3 is 9, plus 3i, plus another 3i, plus I times I, which is I squared. So this gives us 9. 3i plus 3i is 6i, so plus 6i, plus I squared. Now I'll distribute, so I'm having this negative 5 multiplied through to 3 plus I. This gives me negative 5 times 3, which is negative 15, minus 5i, and then plus 2. Well, we're going to combine like terms, but before we do, let's recall that I squared is equal to negative 1. So we'll make that substitution. So we have 9, then we have plus 6i, we have minus 1, minus 15, minus 5i, plus 2. All right, combining like terms, 9 minus 1 is 8. 8 minus 15 is negative 7. Negative 7 plus 2 is negative 5. And we also have 6i minus 5i, and that's just I. So when we're done, we have negative 5 plus I. We have a function f of x is equal to 2 plus x divided by x plus 3. We want to evaluate the function at 10i. So in place of x, we'll substitute in 10i. It looks like we'll make that substitution in 2 locations. So f of 10i is equal to 2 plus 10i divided by 10i plus 3. Now we have to simplify our complex number because that's what we have as a complex number. We want to remove any terms with I from the denominator. So to do that, I'm going to go ahead and first rewrite my denominator so that my denominator is in standard form. The numerator is 2 plus 10i, but the denominator in standard form would be 3 plus 10i. And then I can see my real and imaginary components, or a plus bi. Now to remove I from the denominator, what I'm going to do is I'm going to multiply the numerator and denominator by the conjugate of the denominator. I'm going to change the sign that is between the real and the imaginary components. So I do see 3 plus 10i. I'll multiply the numerator and denominator by 3 minus 10i. So now I have f of 10i is equal to, and I'll focus my attention first on the numerator, 2 times 3 is 6. 2 times negative 10i is negative 20i. 10i times 3 is 30i. And 10i times a negative 10i, well, that's equal to 100, negative 100, I squared. And remember, I squared is negative 1. So now I have negative 100 times negative 1, or 100. So that very last term is plus 100. In the denominator, well, I'll have 3 times 3, which is 9. 3 times negative 10i is negative 30i. 10i times 3 is plus 30i. And I pause and realize that's what I was going for, to get the terms with the I to cancel, to remove I from the denominator. And that's why I chose to multiply through the numerator and denominator by the conjugate of the denominator. Well, let's return to the denominator, and all we have left to multiply is 10i times negative 10i, and we know that's positive 100. Simplifying, we have f of 10i is equal to, turning our attention to the numerator, we have 6 plus 100, which is 106, and negative 20 plus 30i, which is plus 10i. And in the denominator, we have 9 plus 100, which is 109. Well, we're almost done, but I do have one more step. Do you see what the last step is? When I evaluate f of 10i, I do want to write the answer in the form of a complex number, a plus bi. So to do this, the real component would be 106 over 109, plus the imaginary component, which would be bi, which in this case is 10 divided by 109i. And here we have evaluated the function at 10i, and the result is 106 over 109 plus 10 over 109i. Simplify powers of I. Imaginary numbers. Now when we write I squared, this is equal to negative 1. And I is the square root of negative 1. And what we want to do is look at what happens when we take I and raise it to an exponent. So as we start to do this, I is the square root of negative 1. I squared is negative 1. I cubed could be rewritten as I squared times I. You multiply the bases. What do? You add the exponents. So we have an exponent of a 2 and an exponent of a 1. Now I squared, well, that's negative 1. So now I have negative 1 times I, which is negative I. And I to the fourth I can rewrite as I cubed times I. And I cubed we know is what? I cubed is negative I. So negative I times I is negative I squared, and I squared itself, well gosh, that's negative 1. Looks like I to the fourth is 1. So now we're going to continue. We're going to say to ourselves, can we continue to increase the powers on I? So let's do this. Let's go ahead and take a look at I to the fifth. And I'll use the fact that I to the fourth is 1 to rewrite I to the fifth as I to the fourth times I, which is 1 times I, which is I. I to the sixth, I'm going to again use the fact that I to the fourth is 1, and I to the fourth times I squared would be I to the sixth. So now you have 1 times I squared, and 1 times I squared is 1 times negative 1. And do you see a pattern starting to develop? That would be negative 1. I to the seventh, well, here I'll use the fact that, again, I to the fourth times I cubed would give me I to the seventh. I to the fourth is 1, so now I have 1 times I cubed, and I know what I cubed is. I cubed is negative I. And I to the eighth is I to the fourth times I to the fourth. And that would be 1 times 1, which is just 1. And it sure looks like I end up with what? I end up with what? I end up with I, negative 1, negative I, 1, just as I began my cycle. Well, it kind of leads me to the point, which is that when you start to look at raising I to an exponent, these repeat in cycles of 4. So what you see in front of you is I to the first, I to the second, I to the cubed, I to the fourth. And that pattern continues with I to the fifth, I to the eighth, and I to the ninth, I to the 12th. So what we're going to do is we're going to pick an arbitrary exponent, and we're going to go ahead and simplify. So to pick an arbitrary exponent, I'm going to start with, how about we start with I to the 400th. And I want to know 2 things. I want to know if I'm repeating in cycles of what? Cycles of?
Of 4.
Of 4. I'm going to use the fact that I to the fourth is
1.
Is 1 to say to myself, I'm going to decide how many times I can go ahead and multiply that I to the fourth through.
Right.
So I'm going to say to myself, gosh, I'm going to divide 4 into 400.
Okay.
And then I'm going to go ahead and ask you how many times does it go in and what's the remainder? Well, how many times does 4 go into 400?
100.
Okay, so now I have I to the fourth times I to the 100th, and there's no remainder, is that right?
Right.
Okay, and I to the fourth we know is what? I to the fourth is?
1.
1, so now I have 1 to the 100th, and 1 to the 100th is?
That'd be 1.
That'd be 1. All right, so let's go ahead and take a look. Our only acceptable answers, by the way, are going to be I, negative 1, negative I, or 1. Well, let's take a look at 2 more of these problems, and I'll take a look at I to the 2017. That's a great number. I'm going to again use the fact that I to the fourth is 1. I'm going to divide 4 into 2017, and I want to know how many times does it go in and what's the remainder?
It is 504 times and 1/4 of a remainder.
Okay, so when you go ahead and do that division, you get 504.25, is that what's going on?
Right.
Okay, so if you get 0.25, that's a quarter of a fourth, or a quarter of 4, which is a remainder of?
Of 1.
Of 1, very good. So that'd be times I to the first. If I had a 504.25, the remainder is 1. If I had 504.5, the remainder would be?
2.
2.
If I had 504.75, the remainder would be?
3.
And if I had 504, the remainder would be?
0.
0. But we had a remainder of?
Of 1.
We're back on track. Okay, so I to the fourth is what? I to the fourth is?
Is positive 1.
Okay, so I have 1 to the 504th
Right.
times I, and that's just going to give me what? That's just going to give me back a?
I.
I, very good. Again, the only acceptable answers are I, negative 1, negative I, and 1. Let's do just one more. I'm going to give you the problem where we have I to the 4002 and we want to simplify it. We're going to divide what into what?
We're going to divide 4002 by 4.
Okay, tell me what you get.
1000.5.
Let me go ahead and write that I to the 4th raised to the 1000. And then you said 0.5, so the remainder would be?
That would be 2.
2. Very good. And I to the 4th is?
1.
1. So I have 1 to the 1000th, which seems kind of silly to write because 1 to the 1000th is?
1.
Okay. And then times I squared, but I squared is?
Negative 1.
Negative 1. So here my answer is?
Negative 1.
Very good. Thank you. Let's evaluate I raised to the 35th. Now we know I to the 4th is equal to 1. So we're going to factor out as many I to the 4ths as possible. And because I raised to an exponent, the result repeats in cycles of 4, I'll divide a 4 into the exponent of 35. 4 times 8 is 32, and the remainder is 3. So this tells us that we're going to rewrite I to the 35th as I to the 4th raised to the 8th, because that's the same as I to the 32. And since we started with I to the 35th, I'll multiply this by I cubed, and that way the sum of the exponents is 35. Now we know I to the 4th is equal to 1. So what we have now is 1 raised to the 8th times I cubed. And that's 1 times I cubed, which is I cubed. And now we'll just simplify I cubed. We know I cubed is negative I.